Okay, so let's start. Good morning, good afternoon, sorry. Buenas tardes, benvinguts a l'Escola de Camins. Com sabeu, estem iniciant uns seminaris en l'entorn del 50 aniversari de l'escola i aquest és el segon que fem. Ara passaré a l'anglès, perquè en deferència a la nostra convidada. So, thank you very much for coming here. So as you know, we are celebrating in the school the 50th anniversary of the school, so 50 years doing research, science and technology in the field of civil engineering and environmental engineering. And one of the actions that we have planned for this 50th anniversary is to have a series of seminars with top well-known speakers. And this is the series of seminars is engineering challenges that may change the world, trying to connect our knowledge, our research with society, with different social problems. And this is the second one. The first one was related to digital twins and numerical simulations. And in this case, we have the honor to have here the professora PINARDI, that she is going to talk about oceanography and how to connect this science with the societal needs. So it's absolutely well linked with the objective of this seminar. So thank you very much for coming. Thank you very much for accepting the invitation. And I just want to give to Cesar to introduce the speaker, because now you are coming here to listen Professor Pinardi, not to me.
Okay, Esther, thank you very much. Again, Nadia, thank you for coming and for accepting our invitation. Just let me do a very brief introduction to Professor Nadia PINARDI. She is she's one of the most recognized persons in operational oceanography, and of course bridging the operational oceanography, coastal engineering and society involves, of course, the knowing the ocean processes, the coastal dynamics, all the environmental factors, engineering principles, and the challenge is how to link it with society. This kind of approach is, of course, so interesting, important, and necessary to face all the crucial challenges of climate change in our environment and in our society. So this is all what I have to say right now. The speech is going to last around 45 minutes. We will have a session of around 15 minutes for questions, and I encourage you to listen very carefully and to give all the interesting questions that you students of the Civil Engineering School have and can do to Professor Nadia PINARDI. Thank you so much, and you can welcome.
Yes. Hello, good afternoon. Thank you for inviting me. It is an honor to be here for such an important celebration, the 50th anniversary of this important university and department in Europe and in the Mediterranean Sea. So let me go and see what I would like to talk to you about today. I will try to go over some of the new paradigms of thinking that we have to be applied in operational oceanography and more. And then what has happened is a sort of a silent revolution. Some of us, they call it the silent revolution. We have now a system that continuously monitors what is happening at the 1 to 5 kilometer scale at the global and Mediterranean level. And I'll try to make an argument on why this is crucial. And then we are now starting the last mile. We started a long time ago, in fact, especially Professor Sanchez Archila clearly is a leader in this field, which is providing high-fidelity coastal models and digital twins to arrive at coastal resilience and a sustainable blue economy. Okay, so the science paradigms, in my view, we start with the usual, the Renaissance kind of empiricism and descriptive science. And for going to the theory, that was the century after, and then becoming computational last century, the 20th century, and now becoming systemic, holistic, and data explorative. So we are clearly advancing in the methods. And the last one, I have very little to show, even though we were commenting with Professor Sanchez Archila that the developments are very fast. And in 6 months, we almost changed the face of forecasting in the atmosphere and the ocean because of the data explorative, otherwise called artificial intelligence and machine learning. So operational oceanography is a method that makes the basic data for the data explorative science to emerge. And what we do here is that we put together observations, which is of utmost importance. I don't know if you can see, yes. With multidisciplinary, multi-platform observing systems across different scales, from the open ocean to the coast. And we make it real-time and autonomous. The second part is include these observations of the natural system into a digital representation, not digital twin, we are not there yet. And this multi-scale numerical models and AI are now applied, and AI are applied to blue, green, and white ocean components, means the ecosystem, the physical, and the ice component of the sea. And then we do that because we can use practically what was invented in the 19th and 20th century, which is least square methods. So nothing more than that. So we can build best estimates of parameters or fields based upon very simple but essential theory. So operational oceanography started practically 25 years ago, and we were able to advance our understanding of the value chain that is needed to arrive to societal benefit. So it's a long value chain from natural observations to benefit to society. There is a long road. So first is collecting observations. Second is merging this information with numerical models and eventually in the future AI. Then use this information to advance more models, AI-based. And this is a real new part that Europe is developing now, because in order to do that, you have to put attention into accessibility and usability of data. And then last one is customized applications, which in fact, they will give, and they have given in the past, the requirements for all these three parts. So this is the game changer activity that has been consolidated into the Copernicus marine forecasting system. It has the blue ocean, the currents, the temperature, the waves, the sea level, and the white ocean, the ice coverage, the velocity of the ice, the concentration, the icebergs, up to the green ocean, with biogeochemistry. We arrive up to a certain level of the trophic chain. We are not yet covering the whole span. And maybe we will not do it with a numerical algorithm that people had already thought about. So in the Mediterranean, this was part of the work that we did with the University of Catalonia in the past. We started a very complex system, which is one of the most advanced one in Europe, which has 3 components coupled: a component that has the biogeochemistry, the component with the physics, call it physics, and not to call it hydrodynamics and thermodynamics, but this is what it is, and then the med waves. And these are all numerical tools, the ones that were developed the century before ours, quite advanced, and they are run operationally. That means that there is a system to align them to get the best information out of each of them so that you get the best product within a certain matrix. Okay, so this is large scale, as you can see, and the last overview of the development is by Giovanni Copini, that is sitting on the back seat there. Yeah, so now the Mediterranean, the 2 components of the physics are at 1/24 of a degree horizontal resolution, the waves and hydrodynamics plus thermodynamics, which we call also general circulation. Then vertical resolution is about 141 levels, but it's more interesting to know that in the first 100 meters, we have about few meters to 10 meter resolution. And then we have, expect 30 frequency beams within this frequency and 24 directional beams. So it's quite of a solid and resolved system. And attached to that, we have this theory of how to correct the models with observations, which is called the data assimilation. So this is the result of the data assimilation. I'm not showing you anymore the model without data assimilation, because the model without data assimilation would be about 4.5 to 5. Okay? So you really need to correct the model for different sources of errors. We will talk about that. So this is the sea level error in 2 of the most recent systems that we were running for Copernicus. This is not the right number. This is 2016 to 2019, clearly, not in the future. And this is the most recent system, which is still running now. And you see what this sort of, what we call, and you know very well, much better than me, in engineering is progressive refinement system, where you take progressive steps to reach better accuracy. And so what we have to show with this system is that we increase quality between system version. We never go to the next version unless we have a skill improvement. This is the philosophy of weather forecasting. And now it is also the philosophy in ocean forecasting. And here you see errors. I apologize, the colors are not really good as they are clearly on a small screen. But you see the numbers of error in temperature and in salinity. So they are probably among the best errors you can find in the ocean forecasting systems around the world. Now, why open ocean predictions, the one that I've shown you, are a game changer paradigm. This is a wonderful paper by Daggendorf of 2021, where they started to look at sea level extremes around the global coastal ocean. And they were able, by using data, combination of data and models, find what is the signal that gives extremes at the coast, coming from offshore. They call it offshore steric. And this is the local sea level, meaning local winds, local conditions giving. And you see in the majority that is half and half. In some, like the North Sea, not the Mediterranean, but the North Sea is more the offshore steric. Okay, so this is a result. And what tells us is that sea levels at the coast can originate in the open ocean, that coastal signals originate in the open ocean and often very far away, not close. And our gap is that observations and models are not put together in terms of processes and scales yet in an adequate way. We are progressing very rapidly, and I'll show you some examples of success. This is an example of success. We were working with Georgia Tech in Georgia, United States, and here are the main team is CMCC, University of Bologna, and Georgia Tech. And here you see is that this is Matthew, is a hurricane, or Dorian, Dorian hurricane is 2019. It's a very big hurricane that devastated the islands before here, but we are talking about Georgia now. And you see, it arrived on the coast much earlier than that. It was going through this area, which is occupied normally by the Gulf Stream. And so then, here we have our small model, and here we did two things. We said, I put a small model on my coast, but with the rivers inserted, and also I have lots of measurements to calibrate and validate my model. Let's see if I can make it. And so this is the small area that you see, and that's where we do the forecast only. But we have the whole field everywhere in the ocean with a hurricane going by, shifting the Gulf Stream. Okay, so this is the result in our small domain. This is the peak of the storm surge. As you can see, we are doing quite well. The model is a 15% smaller amplitude, but you clearly see it is an anomaly and serious. So if you want to have an early warning system, maybe you catch that. And then, so this is the validation. And having so many validation. But then we said, let's do a Gedanken experiment. Let's do a thought experiment. And let's see, oh, it is Hurricane Matthew. Sorry, I apologize, between Matthew and Dorian, because the paper is about Dorian and Matthew, so I get confused. For both of them, we show the same. So you have this, oh, but this is 2016, so it's good. Okay, so, okay, the example is Matthew, 2016. The previous hurricane, which is identical to Matthew, is Dorian, 2019. Okay, so Hurricane Matthew, this is the peak after I take out the tidal component. So the black one is the total surge. The blue, now that I have the model, I can do this Gedanken experiment. I can take out the winds, the local winds. Okay, so I can erase the local winds and let only the hurricane move in the ocean offshore and entering the domain. And this is what I call sea level from offshore. So I have taken out the local winds. And then the red is the local, I re-add the local hurricane winds. Not re-add, I put only the local hurricane winds and I close my boundaries. So what you see is that the sea level from offshore is 2/3 of the signal. Okay, so this is what Dagendorf was showing. This is what sea level from offshore was called the steric offshore. Okay. The other thing now in Acqua Alta, we had another Acqua Alta, but was Acqua Alta without inundation of Venice. So this was in 2022. In fact, the journalist this morning said, oh, it's too bad you don't have Acqua Alta inundation anymore, because so we cannot talk about Venice anymore. You need Acqua Alta to speak about Venice. Okay, so this is our forecast. This is from the Mediterranean forecasting system that was built all together with a very big Mediterranean community. Now we run it at CMCC, but it was a major effort by all of us. And you see, here is the model with the data, and here we started the forecast. So this is a forecast. And you see the observation, we're telling 162 centimeters. Model gave 161, which is here, and 3 days in advance, because this is 3 days. So what this says, and we do other times, we don't do so good, right? But we says that for that event, we needed the whole Mediterranean model. We didn't need to have something in Venice. Okay, so this is another big important thing. Offshore conditions, everybody knows, are determining salt wedge. This is our salt wedge in Georgia coast. You see how deep the salt enters. We are talking about here, quite near the town. We are 20 PSU, and we can detect salt up to 150 kilometers inside the coast. Okay, so this is another important thing. So now, this global system of currents allow us to arrive at the coast, but we need to have models that can get that information through properly. So this is you see the global, then the Mediterranean is nested into the global, and now we go to the Taranto Gulf, which is this one. This is called the Taranto Gulf. These are the currents. See, this is quite large scale, big ones. These are 20 kilometers across, and then we go. Another model is nested in. Now you see only the models while we go in. And now we go to where the people live, really, and where we can see the currents. Where are the stored currents? In the port here. You can clearly see. You see also vortices, which we know from fluid dynamics exist, but we don't know when they will exist to trap pollution, for example. Now we have it. And, okay. So, high fidelity models. This is our coastal high fidelity models. This is our frontier now. Step one is to use advanced numerical modeling. This is a very nice result, which I want to show you because I did it with a student of mine. We thought about changing the vertical layer discretization. And what we did is we chosen from the large scale, the Z-star system for vertical coordinates that allows us to have 20 centimeter layer in the first with the tides. So, but also it allows us not to get the problems of other coordinate systems, which I don't want to talk about. So this is a simple Z-layer model. This is a river coming off, and this is the plume of the river. We are here in the Po River. And then you see the low salinity water of the river coming into the open ocean, or let's say the shelf. And now you see it with 17 Z star layers, and now you see it with a 20 centimeter Z star layer. So, and now you start to see the right dimension of the layer of low salinity water going. This is the right size, which we measured many times. This is too spread. Okay, so first thing, we need advanced models. Second step is we need to calibrate and validate. So we need observations that are local. This is another model that we have set up. You see, it's a big. It's kind of big. But we wanted to go inside Taranto. And following the thinking that you need to go far away, we don't know how far, we thought of taking this big domain. It's nested into the Mediterranean. And this is what we found. So after calibration, we found, and this is not data simulation, it's just a free run. When the observations are the black ones, and then we have, and this is temperature. This is the coastal model, this model here. And you see this was the Mediterranean forecasting system. Okay, so we have improved, and there are other in this paper. For example, typical, when you have a nested model, you might nest with the tides that are not present in the large-scale model. Sometimes you need to take out the tides from the large-scale models because they're not accurate enough, and it's better to put them in the small scales. And so here you see the sea level from the Mediterranean forecasting system. At that time, we had no tides, so it's flat. And here you see instead observations and the model, which has the tides put in the boundaries here and here, not there. This is inside the Taranto. Okay. Another important point, this is very recent, and is a very important point, is the landward part of the ocean, of the coastal models. We have to extend much farther inside the land than we ever thought before. So this is an experiment they are running in Lazio, Central, at the Tiber River. And this group was able, with the same model that I've shown you up to now, to demonstrate that you cannot use a simple coastal model with rivers imposed at the mouth. So here are the two models. Here is what they call the coastal ocean model, where they put a very small river mouth and they put estimates of the transport, because you really don't know. So somebody in 1999 said that this was the proportion of this branch and this branch, and they use it. But now these unstructured grid models, advanced models, they allow you to go all the way upstream and have the model that give you the flow field and the discharge. And so here it is, the difference in salinity that you detect from by not imposing, without continuously redoing the estimation, without imposing the two branches, but giving it where you know the discharge. which is normally monitored upstream. The discharge in the rivers is always monitored far away upstream. And so you see the advantages. This is purely model. There's no data simulation. Okay, so the CO model is this. This is the model with the 2 branches. Okay, so the message is go include in the coastal model the relevant landward river catchment. And then here, the other step is to understand the uncertainties. So this is another model that we have put in, again, in the Po River Delta. And we started to do ensemble. And you see, very important, this is a storm surge. And you see what happens when you do the ensemble mean is the orange. The observations is the dashed line. So the ensemble mean is better than the single forecast, which is the dark line. So somehow our perturbation, we're capturing the uncertainty. So when you average out the uncertainty a little. There's still uncertainty, but a little. And what is the uncertainty that is giving us this result? So our ensemble was done this way. We had several models on which to nest. We had the one of the Regional Protection Agency, we had the one of MFS, the global model. We had many possibilities. So we used a variety of models to initialize our coastal model. And so we found that the most important uncertainty, which is also called the spread, is the spread is the standard deviation between the models. Using different initial condition and boundary condition was coming not from the rivers, not from the tides, but from the different initial and lateral boundary condition. So that means that if you want to have a very small model in one region, you have to use different realizations to better capture the event. So this is an irreducible forecast error, because we know that our models integrating our equations do not have unique solution. And so we need to find where the uncertainty peaks. Okay, so after doing this and continue doing this, we thought at the international level that we could organize a large decade program that will standardize these methods with all the points that we have said. So we put, this is the name of the decade, the science we need for the ocean we want. And it's kind of an aggressive way to say. I would have preferred for the ocean that allows us to live safely, but it was okay. To be safe, for an ocean, a safe ocean, I would have been better. So we are working, the three, myself, Vili Kurafalu from University of Miami, and Joaquin Tintoré, who is in front of Barcelona, the other institute, and Emma Heslop, UNESCO. And so this is a program that wants to revolutionize our way to do the coasts.
Coastal areas are where most of the world's population lives and where the response to the UN Decade's challenges will have the largest impact. Coastal communities face urgent challenges that are amplified by climate change. Solutions are required on the global coastal ocean level to leverage methods and assets to provide reliable tools to policymakers and managers based on cutting-edge, smart, and efficient technologies that are crucial for the sustainable growth and well-being of coastal communities. A program to develop these solutions, Coast Predict, is a transdisciplinary and inclusive partnership of experts and stakeholders from the world's coastal areas, including island nations. By using the scientific knowledge of the common features of the global coastal ocean, a robust and scalable monitoring and forecasting capability will be developed, implemented at local scales, and applied worldwide. Coast Predict merges state-of-the-art innovative solutions into a single technology and software package, the Coast Predict system. The package will consist of low-cost sensors, new technology, and satellites to observe at unprecedented accuracy and resolution. Numerical models for better forecasting and climate downscaling of the local impacts of flooding, sea level rise, pollution, and climate change, and smart visualizations. These are underpinned with a state-of-the-art information system and best practices fostering interoperability on a local to global scale. This is the science we need for the ocean we all want.
And clearly, this has a strong participation from Spanish scientists. Professor Archila is also, Sanchez Archila is with us, and Joaquin and many others. So one of the issue is how to define and characterize the global coastal ocean. Some people started to do this in 2010, and they took a large view and what I call the offshore view. And so it was defined, the global coastal ocean was actually defined the first time in 2010 in this volume of the sea by Robinson and Brink. And we are starting to have a new definition, which will add the landward part of the coastal ocean. And the coastal ocean, that area extending inshore from the estuarine mouth to the river catchment to the urban settlement, because most of pollution might be originated there on the one side, and on the other side arriving to the Gulf Stream. I've shown you that we have to arrive at the Gulf Stream. Okay, so we defined a three-way strategy. The first is focus areas, science and technology. Definition, what do we need to do? We launched the Global Coast Experiment, where the University of Catalonia participates, Polytechnic Catalonia participates, and then we hopefully will have a generalization solution step. So we launched the experiment last year, but no, not the experiment, the survey to get people to tell us what to do and how to do in their area. And by now we have 120 pilot sites that will try the same technology and see what is working, what is not working. Possibly grouped by characteristics in the coastal area, possibly grouped by major impacts in their area, which is if it is storm surge or biodiversity, and so on. So these are the sites. You see there are a lot in the Med, which is very healthy. It means that, we did a good job with MFS. And, but we have many other areas that have joined. And what do? The process will be also to devise digital twins for these areas. It's among the solutions. So these are where the last part of the value chain. So the process will be stakeholder consultation for each pilot area will be to apply new observations and high-fidelity models, and then simulate what-if scenarios to understand the validity of the solution. So I'm going to show you now 2 examples of digital twin that we did for showing how the method works. So we had a clam farming issue in Italy. And this is a bay where 90% of the clam is produced in Italy. So it's a big, not a big market, but let's say a reasonably large market. And this bay, as you can see, has an opening here only, and but the opening is very shallow. And there are only 2 inlets here that are very narrow, and they go down to 10 meters. So the healthy oxygen-rich waters from outside enter only in these 2 channels. So these people in this area, they think I should dredge these areas, make them deeper, and I will solve the problem of health of the clam farming, right? So they ask us to run our models in this digital twin way. First, we validated the models, and then we run them with the bathymetry modified. Okay? So the surprise was it wasn't so big an improvement. Okay, so let's see the improvement. These people have a health index. This is the health index of now, what it is without the dredging. And so you see that the health index is very high here, but they cannot cultivate here. And then it goes much farther down near the water inlets, where there is, because there are rivers discharging in the bay. Then, when we open scenario 1 is the change of the entrance channel, this one, we get benefit of about 10% on this part of the bay, not that part. Why? Because the circulation does not allow that benefit to go everywhere. Okay, so we needed to see that. They needed to see that. They take the decision. After they took the decision, they did not dredge. So the other one is when we take another change inside the lagoon, they actually have an improvement that is even more limited. That's to be expected. But in some places, this is a nursing area for clams. In some areas, it's even contrary of what they wanted to get. Okay, so this is a digital twin. It's not yet exactly what should be a digital twin, because then I should run the system continuously, and I should get the data to modify my system continuously and so on. But is a rather good digital twin at this point. Then digital twin for nature-based solutions. We have storm surge, in our area. So we put seagrass in our, we asked the question, are seagrass of our area, which is Zostera marina and is Cimodocea nodosa, so they're not, in our area we do not have Posidonia. In other areas of Italy we have, in other areas of the Mediterranean we have, but not in this area. So we put the 20 centimeter long Zostera marina, not half a meter long Posidonia. And we said, is that enough to reduce the energy of the waves? Here is not perfect, because the Zostera is still rigid, so it's still 20 centimeters, but is rigid. Now we have redone with the flexible Zostera. And what we did is we put a seagrass here in front of our area. This is the Po Delta, and here is Emilia-Romagna coastline. We are in this part of Italy. And so we put the seagrass belt here, and interesting thing that I don't have time to show is that depending how you put the seagrass, you get quite different results. So if you follow a system, almost a natural system, which is a sort of a chaotic more system, that bunches and strips are sort of random, you get the best result. And this is the decrease. This is for year 2011, without vegetation, significant wave height here, which unfortunately is not written, and here is 1 year, January to December. When we saw this result, even though we published it, we said, looks very much, too much, right? So we now redid it with the flexible vegetation, and still you get a 40% reduction, not 100% reduction like in these cases almost, okay? But we do. Okay, so the answer is yes. Right, final consideration, sorry if I've taken too much. So, first thing to say is that the past 25 years have changed oceanography and coastal engineering, because now we have operational oceanography giving the background, okay, which is very much what we should do, incremental approach. So we have a first guess, and we added the rest. By the way, for AI, we need to have the background, because AI learns from these data sets. Okay, so it's not only now, maybe in the future, it will not learn from data simulation systems, but it may learn directly from observations. But now, AI learns from these systems. Okay, so from the operational oceanographic systems and products, that's the way it goes. Now, then, if we allow to have new scientific understanding and new products for societal benefit, I hope I have shown you. Operational oceanography at global and regional scales drives the continuous improvement of accuracy at these scales, kilometer scales. We have systems that are always improving, like in meteorology. And now we took the opportunity with the UN Decade Program Coast Predict to finally define the standards. We have so many experiences across. Now we have to find standards. We have to apply it in many areas, across many areas, find the limitations, and find the right combination. Okay? And digital twin are definitely a very important avenue for us for finding the right solutions before we do them, not as we did in the past, that we did not have this whole system built. Now we have an opportunity. Thank you.
So thank you very much for this interesting presentation. Even if I'm not expert on coastal engineering, I think I understand something. So now it's time for questions. So you have any questions, comments?
Yeah. I think I can speak louder. Nadia, thank you so much for your speech.
And I would like to know your opinion on social science, because you were talking also about low-cost instruments and so. Do you think in the future will help us on the validation processes in our models? That's one question. The other is in one of your slides I saw a non-structured grid. Yeah. That's all probably the way of avoiding nesting modeling. I would like also to have. And finally, just a remark, in the lab, in our lab, in the Flume, we, Cesar, Agustin, have had a project, well, two projects, in fact, dealing with Posidonia and the effects on the beaches, so we offer you the data for calibrating purposes, if you, in case of need.
Thank you. I mean, they're all very relevant questions. About citizen science, we actually focusing cost predict on citizen science because we think that that is, I've shown you for Matthew or Dorian, this was a citizen science network which was built by the schools around the area. And in the paper, we show the comparison of our model in the marshes, because that's a marsh area. And they put all these sensors to measure the 5 millimeter water that arrives there. And it's amazing how much trust you have in your model when you see the comparison, since your model can inundate and you can find out. So citizen science, in my opinion, will be one of the low-cost sensors, low-maintenance sensor, coupled to satellite high resolution, which we also don't use enough, I think will be the system for the future in the cost, to tell you the truth. We need to have few validation stations that are expensive, maybe, like we have now. We have the tide gauge stations, very expensive, high maintenance, but the rest, yes, is all citizen science, in my opinion. Okay, so the other part were the unstructured grid. Yeah, so there is not only the question of being able to refine the grid where you are, but there is a question of adding details by the local experts, which should be always considered. When you run a global model with intensification, maybe is a better initial condition for another model that is run locally and has maybe a better bathymetry, because I mean, we haven't spoken about bathymetry here, but bathymetry plays a very big role. And bathymetry is not steady. I mean, it's also dynamic. Okay, so I think the nesting approach will remain. In which exact form? Maybe starting from another unstructured grid at the global level, maybe. Actually, we are trying that, to have a global unstructured grid model, and then another unstructured grid. But the key is that we have to show always improvement. So when we when we say this model is better than another, we have to see for what is that it is. And I think a nesting approach has the advantage in that you can show, you can get improvements. The third one was? Oh, that's a very important offer, because actually I think we are doing, and I thank you very much. Actually, what we should do is actually a group between the people in Fiumicino, not Fiumicino, but in Civitavecchia, exactly, in Civitavecchia, where we are looking at actually the couple Posidonia, because that's a Tyrrhenian part, so it's like the northern Mediterranean where you are. Posidonia, and we have corals coralligenous. So it is half rocky and half sand. And so what we found is that this combination, which was a natural combination, may be a very important one because the coralligenous rocks, they're actually defending the Posidonia, because the problem with Posidonia is that if you have a real strong storm, they will go. But it is interesting to know that naturally, in Italy, at least, in that area, there is coralligenous rocks and then Posidonia. And so we thought of putting Posidonia in front of the coralligenous rocks, and we immediately changed and went to the other. So it would be nice to see if in a region where you don't have coralligenous rocks, it will be the same effect, and definitely. It will be fantastic. Yeah, thank you. Thank you for offering. I think the other people will hear you better.
Okay, thank you, Nadia, for your talk. I have a question about the cost predict. I think it's a very good initiative. We are involved in that initiative. However, you mentioned, and here it's written, that you will try to define standards for the development of coastal models. However, our experience in our life is that the coastal area are completely different. How you face, for instance, a salt wedge that we are thinking in non-hydrostatic model, or how you face the problem of urban beaches, or how you face the port forecasting. So do you think that it's possible to define standards as our coastal areas are completely different in terms of physics, and also in terms of requirements for the stakeholders? Thank you.
That's a very important question. So we think of, as I said, defining several standards. Maybe collecting the standards for a certain type of coastal area. And maybe the same components of the standards may be combined in a different way in another area, or maybe in another area you need something more. Let's say, if you are in a port or you are in a natural beach, it's very different, right? And so in a port, what we would like to do with Coast Predict is to say, you can have a lot of citizen science done because you have a lot of population. You should use citizen science, and then this will calibrate in details the models. If you are in the natural area like this one, you need also citizen science, but you need, mostly a detailed understanding of the natural vegetation. You need other things, right? Now, if the model that I use in the natural area is different from the one I use in the port or in the river, as I said, we have to have a suite. But we have to say, when you have a river that is your major driver for your coastal area dynamics, whatever it's sediments, then you should have, the best one you have to choose is a non-hydrostatic model, for example. We can say that if we have the data, if we have observations. So what we want to do, we haven't decided yet, we are discussing now at the level of Coast Predict. We want to do the same system in different characterized areas and different systems in equal areas to see if it is possible that, you have overdone or there is something lacking. So the principle by which we put together the standards it has to be defined. So it's still on the way. It is certainly not an evaluation of the models, as numerical tools, more accurate, less accurate. It's with respect to the reproduction of many events. That is, I think, different from what it was done before. And if I might say another thing, we are also trying to couple the first classification that was I show you with a new classification that has been done by ecologists, where they took the whole world ocean with satellite images, and they classified on the basis of several parameters, segments of the coastal area. And you find, so we want to, under an offshore area, you have many coastal segments, and so that offshore regime will be different in that area. But we want to try to couple the two, the classification of the segments with the offshore, and then the system that will monitor. So, I mean, it's UN decade, so you have to do something that has not been done before, and your suggestion is proper. How to assemble the standards. Yes.
Hello, Professor. First of all, thank you very much for the talk. I think it was very inspiring for us as students. And I have a question. We're in a master called COMEM. We come from different parts of the world, and we were just talking, and we wanted to ask, how are you expecting to reach different parts of the world, considering that data has to be gathered in different parts, and also that different models have to be run at different locations, at different scales? Are you expecting to collaborate with universities or with different companies in different countries?
Very good question. So, this is actually one of the major innovations that we want to try to implement. The data management system that will allow to be very interoperable between places. I mean, it's a bit of a deviating answer to what you were asking, but let me try to arrive there. So, it is true that it's very difficult to have a data sharing environment which is fragmented in many institutions and with many places around the world. So we are sponsoring, as a Coast Predict, a cloud computing platform which will host many pilot sites. And so we think that actually one of the barriers to exchanging data can be removed by using cloud computing. We are talking, I don't know if you ever use something like Google Earth Engine or a planetary computer by Microsoft, where you actually work and you have sharing of tools across different regions. Now, this is going to be difficult to begin with models run on the cloud, because you need a computing facility, computing resources, not only storage resources. So we said we first privilege storage resources in a computing framework, and then we run the computer on our own computers and we upload. So it's still a bit, we think of phases of development. But the way to, at the end, in 2 or 3 years, I think also our models will be run on the computing cloud. And AI will be done on the computing cloud. There is no need to do any more this exchange of data, which normally privilege us and does not allow developing countries to get the same efficiency and turnover. So I think it's like working on a dream. I don't know if you know Bruce Springsteen, but Bruce wrote this wonderful music that is, I'm working on a dream, and it seems very far away, but if we work all together, we might arrive there, and if it is right, we will. So CostPredict is trying to sponsor cloud computing as a way to remove barriers, running models, accessing data, and so on. It's a bit of a overall answer to your question, but this is the technology that now we have not used enough to share the data, and clearly requires a lot of good data management principles, and we want to start from the beginning with data management. That is what is our thinking. So we will form subgroups of people, maybe, but working with the same standards on cloud computing. Okay. Please.
Thank you for your talk. Very nice and very interesting. I have one question that comes from the land side. And looking at these more detailed models that you have in different areas of the coast, and you mentioned in some of the slides that the idea at some point is to include biochemical processes in all these models. Have you discussed how do you expect to include groundwater discharge in all the coastal processes?
Yeah. So there are a few groups that are attempting to connect these. Okay, so our plan is to have catchments, surface waters, coupled fully with the ocean for the time being. Okay, so precipitation arrives, then there is the model grid the same as in the ocean, but now is on the land, and then you get the sliding of the water, and so. But we need to get the underground, and so some people are attaching to the continuity equation of these models that are conserving water, arrives from the precipitation, and then it remains there, only redistribute to get it into the underground. The underground, though, is really a frontier, because how to do that? I mean, you can do it with, up to now, the best models in meteorology, they do it with buckets, things of this kind. No, you can go and get more sophisticated models, but they've never been coupled to unstructured grid for the surface flow. So, which couples to the coast. So I would say that this is really frontier, and that it should be tried. It should be tried with the understanding that the surface flow field will all be in one model. There will be no more limits to where the water is no salty and when it becomes salty. Okay, so that will be all done. But how to put that into the subsurface, which is a very important societal benefit problem, still, I know very few groups that are trying to do this. Obviously, there is a DHI, there is a, what is the name? The Deltares and all the models that have been in the past. But, they are not so general and they are closed. So you don't know what it is really in them. They're very commercial.
I'm gonna say the same than before. We are working on that. Okay,
Wow.
the groundwater hydrology group and the laboratory engineering
And we
laboratory.
have an
are working.
hydrology group also starting, smaller.
case.
No, but we should, this is a very important part. We might have, to specialize some cases of cost predict, at least to brainstorm on what is needed, given the surface flow.
We have been working on that 10 years, and we are still starting in many things. It's a big challenge, really.
Very nice. I mean, this is a very nice, yeah, definitely. Very important. I don't know why the underground is not funded the same. The underground is funded. What we are trying to do is use adaptation fund resources to work into the pilot sites, because you can do an European project, but you do it only for Europe. Yeah, you can have a test case, but it's very, so maybe in that case, it's much easier to have this, because the people of the region, they really are affected by salting of the aquifers. And they are really, even in the Med, but it's impossible. It's something that people don't have in their mind. They don't think is what they should put a lot of attention. We started a long time ago, we wanted to do an investigation in the Sicily Strait. Sicily Strait is a very special place. Sicily has a lot of underground water coming off from the side of the land, and it's fresh water, and has a lot of nutrients. So there is a very special ecosystem there that is connected to that springs that are coming out. And then now people see differences in the ecosystem. They're related to that, a change in the waters that are coming off. But still, very few are working on that issue, correlation. So this is, maybe I think Cost Predict is the right platform to try to add that. It's actually mentioned. You have, some. Maybe we should get their names and add them to the huge mailing list that we have. But it is on us to. Also, we need, yes, this is what I wanted to, very nice. Thank you for. Yeah. Okay. And the other thing is, this year or next year, we have to have an ECOP. ECOP is Early Career Ocean Professional meeting. And we would like to invite really young postdocs. You don't say young, because I just take it away, it shouldn't be said. Is young professionals. And if you go on the UN Decade, there is a very big movement. Most of you can fit in, and it is a movement that we need to foster, okay? So you can drive in a certain direction. You are allowed, not only, you should drive in a certain direction, what we are doing. This is the difference of this decade from the remaining. This decade has participation from a lot more people than few scientists. And so it is a lot. So we need to get our ECOP, cost predict ECOP has to be increased. If you go on our webpage, you find way too little people that receive our mails and are aware of what is happening.
Just the last one, because I think we have no more time, we are too late. So just one question, and then you can continue the discussion later. So the last one.
We just made a new group that is led by South Africa, and that looks for nature-based solutions into integrated coastal zone management and other issues. So please join on our web and write to us, and then we will include you, and we'll try to make as much as possible early announcement of workshops where we discuss this.
Okay, so thank you very much. I'm sorry because we just need to cut because this is also recorded and there's a lot of other people waiting. So thank you very much. I think it has been a very interesting conference. That's why there is a lot of questions. I'm sure that you will continue the collaborations with UPC, with different groups. I'm expert on a steel structure, so we can find something. But anyway, thank you very much for coming. Thank you very much for attending the conference, and see you next time.
Thank you for the invitation.
Thank you. Thank you.